All right. So once there is an external force, okay, then the body accelerates. Once the body accelerates, then it means that there will be a change in velocity because Newton's second law, rate of change of momentum is directly proportional to this. But once the mass is constant, but when the body accelerates, its velocity changes. The change is an increasing one. So m into brackets v minus u all on t. That's the reason for which we talk about change in momentum, because the velocity can change, but the mass of the body, no matter the situation, is always constant. So we say that F is equal to delta P on T. Now, F, when we cross multiply, F times T is equal to delta P. The product of the force and then the time is what we call as impulse, I. This is impulse, capital I, which we call as impulse, is equal to the change in momentum. And so we said that impulse is equal to change in momentum. What it also means is that I, which is impulse, is equal to F times T. Now, the greater the force acting on the body, and then the greater the time taken to act on the body, the greater will be the impulse. So when force is great or larger, and the time taken for the force to be exerted on the body is also great, then the impulse is equally great. So impulse is equal to a change in momentum. I is equal to mp minus u. Please, are we okay? And we are deriving this from Newton's second law of motion. From Newton's second law of motion. Okay, before we go to application of this in solving problems, let me ask this question. Please, if a body has a greater momentum, what does it mean? If a body has a greater momentum, what can you say about the body? Priscilla, let me pick your brain on this. Priscilla, if a body has a greater momentum, what can you say about the body? Priscilla, are you there? Oh, Priscilla seems to be. Adwa, if a body has a greater momentum, what can you say about the body? Hey, okay. All right. Priscilla, I've heard you.
Yeah.
Let me sound. Hello.
So I think now means to have a greater,
It will have what?
like its velocity will be great.
If a body has a greater momentum, what can you say about the body? You said its velocity will be great. Okay, that's what Adwa says. Yes, somebody else must come in.
Hello. Okay,
Uh-huh.
hello.
Priscilla, come in.
Please, can you hear me?
Yes, I can.
Okay.
All right. Now, if a body has a greater momentum, what it means is that then the tendency for the body to continue to be in motion is greater or larger. So a body with a larger momentum or a greater momentum has the tendency to continue being in motion. So a body with a greater or larger momentum has a tendency to continue being in motion, or a greater or larger force. This is all. A greater force is required to stop a body with a greater momentum. Practically, this is it. If I should solidly hit a tennis ball with a bat, if I should solidly hit a tennis ball with a bat, and then the same tennis ball, the same mass, throw it with the hand, which of these situations, okay, would inform the chances that the tennis ball will be stopped? Or in which of these two situations can somebody stop the tennis ball? A tennis ball solidly hit with a bat, okay, and then as a tennis ball, the same tennis ball thrown with the hand. In which of these situations can it be stopped? Yes. Anybody?
The tennis ball thrown by the hand.
Why? Why do you think so?
Because the force acting on it is not too great compared to that of the bat.
Why?
So
Resi, why? Why do you think the force isn't too large?
because it's having a low speed.
Exactly. The same tennis ball, same masses, but with concerning the one solidly hit with a bat, it has greater speed or velocity, meaning its momentum will be greater. Now, looking at the same tennis ball being thrown with the hand, throwing the ball with the hand wouldn't give it much velocity, and so its momentum would be less. Now, once the one that is solidly hit by the bat has a greater velocity and so has a greater momentum, the chances that it will continue to be in motion is great. It is great because it has greater momentum. So a body with a larger momentum has the tendency to continue being in motion. Another example, look at the same tennis ball and then short put. I'm sure you all know what a short put is. That short put ball. Okay, throwing a short put and then tennis ball with the same velocity, the chances that you cannot catch the short put is greater than catching the tennis ball, because of the mass. The shot put has a greater mass than the tennis ball, even though the two move with the same velocity. So that is the meaning of this statement. Please, any question? All right. Let's solve one or two questions on momentum, and then we continue from there. I'm going to send about two, three questions onto the page. Please, I'm coming. Sure. I'm coming. Let me take a shot rather and put it onto the, and then the last question, I 100 kilogram mass, 100 kilogram mass with a velocity 30 kilometer per hour. 100 kilogram mass with a velocity 30 kilometer per hour. Okay, so 5 seconds, just give it a try. A 4 kilogram mass with a velocity 0.5 meter per second. 80 gram mass, a velocity 6 meter per second. 100 kilogram mass with a velocity of 30 kilometer per hour. Find the momentum in each case. 5 minutes. So your time is 1:27. 1:27. Okay, so with a velocity of 0.5, therefore, the momentum of the body, yes, Adwa, what did you get for this? What did you get for the velocity, the momentum of a body, 4 kilogram velocity 0.5? Yes. Adwa,
He had to.
you had 2. 2 what? 2 what? Units. Very, very important. Okay, so the mass is 4. The velocity is 0.5. 0.5 is 5 on 10. Okay. So this is, yes, 20 on 10, giving us 2 kilogram meter per second. Adwa, the unit is very, very, very important. The unit is very, very, very important. Please, how many of you got it? Got 2 kilogram meter per second? Yes. Okay. I'm sure a lot of you had this correct. The second question. The momentum of a 7 kilogram mass of velocity, 80 gram mass with a velocity of 6 meter per second. So 8 gram mass. You see, over here, we must change the mass into kilogram. We must change the mass into kilogram. So 80 divided by 1,000 in kilogram times a velocity of 6. Okay, so we have 86, 8 times 6, and that is 48. 48 divided by 100, which is 0.48 kilogram meter per second. Yeah, show by hands those of you who got this. If you got this right, let me see you and perhaps clap for you. Okay. All right. More hands, oh, I need more hands. Okay. Then the last question. Mass of, we have a mass of 100 kilogram, velocity of 30 kilometer per hour. So V is 30 kilometer per hour. Let me ask one of you to take us through how you were able to go around this question. Okay, Akuya, how did you solve this problem? Akuya, a mass of 100 kilogram. So the mass is 100 kilogram and a velocity of this. Akuya, are you there? Oh, okay, then Chrysler.
Yes, please.
How did you solve this?
Mr. Edia, please, I changed the 30 kilometer per hour to meter per second.
And how did you do it?
I divided 30 by 3,600.
So this is okay. So 30 kilometer per hour, 1 hour. And so we must, since this is given in kilogram, then we must change the velocity too. So we change 30 kilometer to meter, and 1 kilometer is equal to 1,000 meter, and 1 hour is equal to 3,600 seconds. Okay, so we have 1, 2, 1, 2. So we have 300 on 36. And what is 300 divided by 36? 300 divided by 36.
8.33.
8 points. 8 points.
3.
Okay. Okay, so 3. This is meter per second. Therefore, the momentum P would be equal to the mass, which is 100 times velocity, which is 8.33. And so we have 833 meter per kilogram meter per second. Let me see by hand those of you who got this correct. If you got this right, let me see you. If you got 8333. Okay. All right. So this is
Mr. Edia,
how. Hello.
please, the conversion, I did mine a little bit different from this one,
Did you get the
but
same answer?
now I'm a little bit confused, but I got the same answer.
How did you do it?
I did mine 30 kilometers per hour is equal to 30 on 1 times 1,000 meters on 1 kilometer times
Erase it.
1 second on 3,600
Okay.
seconds.
You see, this is how to do it. Like 30 kilometer per hour means that we have 30, this is it, per hour. Okay, this is equal to 30 kilometer over the per. Raised to the power -1 means that if you want to write it in fraction, there is it. So it's simply 30 kilometer over 1 hour. So I convert, this is distance, this is time, given as velocity or speed, okay? So convert the numerator, which is the distance to meter, and 1 kilometer is equal to 1,000 meter. So if 1 kilometer is equal to 1,000 meter, okay, so if I have 30, why, how much, or what will be the equivalence in meters? If one kilometer is equal to 1,000 meter, then this will be 30 times. Okay, then I come to the denominator, which is the time. I'm converting, I have 1 hour per hour. 1 hour to seconds. And I know 1 hour is equal to 3,600 seconds. So I divide the distance in meter, the time in seconds, and that's it. This is simpler than 1 kilometer per hour is equal to that. Okay, so please adopt this.
Okay.
Is that okay?
Okay, so thank you very much.
Welcome. All right. Another question. Hold on. Let me get you the second question. I thought I had them to share with you quickly, but all right. Are you ready? A force of 8 Newton acts on a body of mass 4 kilogram. A force of 8 Newton acts on a body of mass 4 kilogram for 0.3 seconds. A force of 8 Newton acts on a body of mass 4 kilogram for 0.3 seconds. I, what is the change in momentum? I, what is the change in momentum?
Mr. Dia, please can you start again?
I can. A force of 8 Newton acts on a body of mass 4 kilogram for 0.3 seconds. Can we continue?
Yes, please.
I, what is the increase in momentum? Oh, sorry, change in momentum. I. If the body was originally traveling at 5 meters per second, if the body was originally traveling at 5 meters per second, what is its final speed? What is its final speed? Then I. How far will it travel in this time? I. How far will it travel in this time? A force of 8 Newton acts on a body of mass 4 kilogram for 0.3 seconds. I, what is the change in momentum? I. If the body was originally traveling at 5 meters per second, what is its final speed? I. How far will it travel in this time? So make me proud. Go through it in about 5 minutes. Okay. Go through it within about 5 minutes. Let's see what you can produce. Then I also add on. It is
Yes.
delta P is equal to impulse, and impulse is the product of the force and the time taken for the exertion of the force. Okay, Akosia, go ahead.
And the force was given as 8 Newton. And the
So
time as 0.3
8
seconds.
times 0.3. 0.3 is 3 on 10. So this is 2.4
2.4.
kilogram
8.4.
meter per second. So the change in momentum is equal to the impulse. Okay, another volunteer to come in. If the body was originally traveling at 5 meters per second, what is its final speed? Yes? Who would want to take us through this one? A volunteer. Somebody should volunteer. Else I'll call you. Who is volunteering? Len, are you there? Okay, I'll let somebody else come in, okay? Len, are you there? So many Millicent. Oh, I have a lot of you here. Okay, Amma, over to you. Question 2. If the body was originally traveling at 5 meters per second, what is its final speed? Go ahead.
Okay, so the question has given us its initial velocity, which is
Yes.
5 meters per second. So
Yes.
the formula, force is equal to change in momentum over time. Yeah. So force will be 8 Newton. So 8 is equal to, the mass is 4 kilograms. So 4 times velocity, which we do not know, minus 4 times initial velocity, which is 5. And that will give us 20.
Amma, I have the
So,
idea. You have the idea.
yes.
Let me take over. Okay.
Okay, sir.
Don't forget, he said change in momentum is equal to the impulse. So meaning I is equal to delta P. And what is delta P? Mass. This is about the same mass. So it is constant. V minus U. So there will be changing momentum because the velocity of the body is changing. Okay, so simply all that we need is this. I is equal to this, where I is the impulse, which we've calculated. Impulse is equal to change in momentum. And so 2.4. I is 2.4. So we have 2.4 is equal to what's the mass? The mass is 4 times V, the final velocity, we don't know, which we are looking for, minus the initial velocity is 5. Finished. That's all you find for V. Okay, by dividing through by 4. So you have V minus 5 is equal to, what is 2.4 divided by 4? 2.4
0.6.
0.6. Therefore, V is equal to 5 plus 0.6, which will give us 5.6 meter per second. That's the final velocity. Plus, are we okay?
Yes, please.
All right. Please, if you don't understand something, do not swallow it. I'm here. This is our physics lab.
Yes.
Akosia, Adoma, Jema, go ahead.
Mr. Dear, please. Is this the only way that you can use to solve it?
Oh, you can ask, you can use several ways as Amma was suggesting. Fine. We know F is equal to delta P over T as Amma was saying. But the delta P is, we know delta P to be mv minus u, since the mass is constant. So when you put that there, you have mv minus u on T. You have F, you have T. But you see, when you do that, the force, when you do that, it's a repetition of what you have done, because you have found change in momentum. Okay, so when you put 5 here, or the force is 8. Okay, 8 is equal to mass of 5 v minus, sorry, the mass is 4. Mass of 4 v minus 5 over 0.3. It's a repetition of this same thing you've done here. Don't forget, whatever you've calculated is F times T. This times this. Akosia, do you see it?
Yes, please.
So when you go through it, you have these figures already. Relate and then move on. All right. The last question. How far will it travel in this time? How far will it travel in this time? A volunteer to take us through. Who would volunteer? I have 16 of you. Okay, 15, including myself. Who would volunteer to take us through this? Else I'll call you. Hey. Yaba. Yaba, you in the building? Nana Equia Frempong. Nana Equia. Are you here?
Yes.
Nana Equia, can you take us through the third question? We are looking for how far. It's about distance. Can you take us through?
Okay. Simply, I used the formula V is equal to S on T.
Come again.
V is equal to S on T.
Uh-huh.
So we make S the subject.
That is VT.
So S is equal to 5.6 times 0.3.
Okay. All right. You see, let's see when to use this and when not to use this. As we go through the question, we realize the body accelerates, isn't it? Does the body accelerate, class?
Yes, please.
What is acceleration? Rate of change of velocity with respect to time. So we realize the velocity is changing from an initial value to a final value within the given time. So there's an acceleration. Now, Nanepia, my question is that you use 5 point, the final velocity. When you do this, all that you are saying is that the body covered this distance with a constant velocity of 5.6. Nanepia, do you see it? You are telling
Yes,
me
please.
that the velocity of the body is constant from start to finish. But that is not the case. The body accelerates. Okay, so when you are dealing with an acceleration, please, you don't use this. You have to use one of them. V squared is equal to U squared plus 2AS to find the distance. Or S is equal to UT plus half AT squared. You have to factor the acceleration of the body within the given time. When you use this, it's as if you are dealing with a constant velocity kind of motion, meaning the velocity from start to finish is constant. That's the difference. Okay.
Yes, please.
All right. So let's find the acceleration of the body. A is equal to V minus U on T. Therefore, we have 5.6 minus 5 divided by 0.3. And this is 0.6, aka 6 on 10, divided by all times 10 on 3. The acceleration of the body, therefore, is equal to 2 meters per second squared. A is 2. If A is 2, then we can, so 5.6 squared, this is U, minus 5 squared is equal to 2 times 2 times S. Therefore, S is equal to 5.6 plus 5 times 5.6 minus 5 all on 4. Okay, I just want to apply mass to. So this is 10.6 times 0.6 divided by 4. And do that calculation for me. 10.6 times 0.6 divided by 4.
Miss Asia,
1.59.
Hello.
please, which formula are you using?
Oh, I just use the third equation of motion. V squared is equal to U squared plus 2AS. Okay, but I'm just using difference of 2 squared to, and the answer is what? 1.59, isn't it?
Yes, please.
So this is 1.59 meters. Let's also use the other formula to see if we can get the same thing. When we use the second equation of motion, S is equal to, let me adjust the screen. S is equal to UT plus half AT squared. What is U? Our U is 5, T 0.3 plus half times, what is A? Acceleration is 2 times 0.3 squared. So this is 1.5, 3 on 10. 1.5 plus 0.3 squared. Okay. 1.5 plus 9 on 100. Please calculate that for me. So this is 0.09. 1.5 plus 0.09 is equal to 1.59 meters. Please, do we see it?
Yes, please.
So whichever way we go, water would surely reach you. So please, whenever you have two velocities, note that then there is an acceleration. or a deceleration. And so you must know what to use in determining something. Please, any question? If you have any question, quickly ask before we move on. If there is no question, then I'm going to. Do I clean the board?
Yes, please.
All right. Let's look at the law of conservation of linear momentum. We use linear because we have angular momentum as well. So the law of conservation of momentum, or if we want to qualify it well, linear momentum. Conservation of linear momentum. I'll give you background information before we quote the law. You see, if you are firing a gun, you haven't fired any bullet before, but you do watch war films. So let me draw your attention to what you've been seeing in war movies. If you are firing a bullet and you are an amateur, if you are not a professional, you can always misfire, because it is said that firing of bullets, let me use something to illustrate. Firing of bullets is always said that as you fire, there is a reversal force on you. So as you target to fire, if you are not careful, the moment the bullet leaves the nozzle of the gun, the direction will change and you can always misfire. This is because of momentum. It's also based on Newton's third law of motion. To every action, there is equal and opposite reaction. Another point where conservation of momentum also comes in is the launching of rockets. Rockets are launched to space as a result of, you see, the rockets are filled with fuel. Now, as the fuel burns and then leaves the opening, the exhaust, there's a nozzle, just like the car exhaust pipe. So as the fumes, the burnt exhaust fumes escape with that great velocity, there is a reversal force on the rocket, and that is what propels rockets up. So long as the burning of the fuel within the engine continues, there will be an exertion of upward force on the rockets. So exhaust or fumes escaping in one direction, and then its reversal impacts on the whole rocket. And that is what, as I said, that is what propels rockets to space. Another application of momentum is that whenever you are in a boat and you want to step from the boat and then land at the shore, if you are not careful, you will fall back into the water or the river. The point is that as you attempt to step out of the boat exerts a contact force on you, okay, to help enable you step out of the boat. In the same way, you also exert a reversal force on the boat. So as you are aided by the boat to help your stepping out, you are also aiding the boat to just move back. And so if you are not careful, this action and reaction thing would eventually drop you into the water instead of stepping onto the shore. I have witnessed a situation where somebody sitting behind an Okada man felt that one Okada, okay, I think moved past theirs, okay, in a bad manner. I've forgotten the term, but so he felt he would punish the Okada man by just as pushing or kicking at the other motorbike. As he did that, both of them ended up, okay, dropping to the floor. He forgot that as you exert a force on one, there is equal and opposite magnitude of force also exerted on yours. And so this is the practical situations of conservation of momentum thing. In physics, whenever we talk about conservation of something, it's basically about what happens to a particular situation before and after an event. Okay, when we are talking about conservatory thing, we are looking at a system and what happens to it before and after the occurrence of a particular situation. So energy conservation, we are looking at the energy before, energy after, and so on and so forth. Now, let's look at somebody stepping, or let's use Newton's third law of motion. We'll use both second and third law to prove or to derive expression for conservation of momentum. But these are two bodies that are involved in some kind of interaction or collision. The body A exerts a force, body A exerts a force Fa, and then body B also exerts a force Fb. So this is A, and then this is B. So the two bodies exert equal. So Fa is equal to Fb, but they act oppositely. So let me bring a minus here. So this is similar to a situation where two cars are in a head-on collision. Okay, in a head-on collision, one body exerts a force and the other exerts a force. By this time, we are looking at the two forces to have equal magnitude. So Fa is equal to Lb. Are we okay? Please, are we there? And because their
Yes.
directions are opposite, that is why one is negated. You can look at this to be positive and then this to be negative to denote that their directions are oppositely. Now, Fa is equal to mass of A times acceleration of A. So acceleration A. And what is acceleration? Acceleration is related to change in velocity. So ma times the final velocity of A minus the initial velocity of A divided by time. The time for the impact is the same. Ta is equal because they are in a state of collision. So they collide at the same time. Okay. So Fb is also equal to m of B, mass of B, times final velocity of B minus the initial velocity of B over T. I said time for A and time for B the same. Now, if we apply Newton's third law of motion, that FA is equal to magnitude of FB, but opposite. So let's substitute whatever we had for FA, whatever we had for FB. So MA VA minus UA over T is equal to negative. Don't forget we negated B because of the different direction. Negative of MB VB minus UB all on T. If we multiply through by time times T at both ends of the equation, the time cancels out. Please, are you following? Are we okay?
Mr. Dia, please, can you take it from
Please
the
come
text?
again.
Yeah.
Okay. We are looking at two bodies, A and B, that are just colliding each other. So body A and then body B, this is A, this is B. They are in a state of collision. So A exerts a force FA on B. And then B also exerts a force FB on A. This is similar to somebody stepping out of a boat. Okay, the boat exerts a force on the person, and the person stepping out of the boat also exerts a force, okay, on the boat. Both forces are equal, but their directions are opposite. Okay, so let's use the two bodies colliding example. Okay, so what is the force?
Dia,
Hello.
please, can you bring your camera down a bit so I can write the one down there?
I'm going over the same thing. So, okay.
Okay. Yes, please.
So, since we are saying that by this symbol, we are saying that the two forces have the same magnitude. So, FA, magnitude of force A is equal to the magnitude of force B. But their directions are opposite. One of them is to the east and the other is to the west. So we negate one of them. So we can say that FA is along the positive x-axis and FB is along the negative x-axis. And so that is denoted by negating one of them. Are you okay here? Are we okay?
Yes. Yes.
Okay, we know force. Force is equal to mass times acceleration. So here we are using Newton's third law of motion. Newton's third law of motion. We are using the third law to prove something. We are using the third law to prove something. And that is what you understand later. Force is mass times acceleration. So if we want to determine FA is equal to the mass of the body A, this is MA, mass of the body A times the acceleration of A. But acceleration, we know, is equal to final velocity minus initial velocity. So this will write as final velocity of A minus the initial velocity of A, all divided by time. That will give us FA. Let's do it for FB. FB is equal to mass of B, mass of the body B, MB, times the acceleration of B. But acceleration, we'll write it as this. So VB minus UB all over T. Please, are we okay? Are we okay?
Yes, please.
So we are going to substitute all that we've had for FA and FB into the Newton's third law equation, which we earlier, okay, established. So MA VA minus UA over T is equal to minus of FB. But FB is this. FB is MB times VB minus UB over T. Now, when two bodies collide, the time taken for the collision to take place is the same. Look at this. The calculator and then the duster. When they are moving in opposite directions, so when they collide, the time taken for the collision for A and B, the same. So T for A, T for B, the same. And so when you multiply through by time, it can easily, the same magnitude, it can easily cancel out. T will be cancelled from each side of the equation. So we have MA VA minus UA is equal to minus MB into bracket VB minus UB. Class, are we okay to this step?
Yes, please.
Okay, let's expand the equation. So MA VA minus MA UA is equal to minus MB VB. Will this be plus or minus? Will this be plus or
Yes.
minus? Plus
Plus.
Plus.
MB UB. Now group all the V's at one side and all the U's at one side. Okay, so let's bring this. Let's bring the V here, because we are bringing all the V's to one side and all the U's to one side. This is negative U. It will take it to the other side so that it will be positive. So, and then this is negative MBVB. We'll bring it to this side. So MA VA, we are bringing this V. So plus MB VB is equal to, this is already plus. This is already plus. So MB UB, this is negative. This is U. It has to go there, but it's negative. So plus MA UA. Now, in mathematics, this is an equal to. You can choose to bring the right-hand side before the left-hand side one. So let us do that. Let us bring the right-hand side to the left-hand side. Later on, you understand why I'm doing that. So MB UB plus MA UA is equal to, then I'm now bringing the left-hand side to the right-hand side. So the V's, MA VA plus MB VB. Now, please, class, what is this? What is MA times U? I'm sorry, what is MB times UB? What is this term? MB times UB. Anybody? You see, what is momentum? Momentum is mass times velocity. But this is mass of B times the initial velocity of B. So this gives us the initial momentum of B plus MA, UA. This is initial momentum of A is equal to VA. This is the V, final velocity. So this is the final momentum of A plus final momentum of B. And this is the law of conservation of linear momentum. What does it say? The law of conservation of linear momentum says that, or states, in the absence of any, I'll give it to you, but I'm just going through because of what we've derived. In the absence of any external force acting on a system of colliding bodies, in the absence of any external force acting on a system of colliding bodies, the sum of momentum before collision is equal to the sum of momentum after collision. That is the law of conservation of linear momentum, that in the absence of any external force acting on a system of colliding bodies, when you have bodies that are in collision, that are interacting with each other, when there is no external force acting on them, then the sum of momentum before collision is equal to the sum of momentum after collision. And that is what we have established using Newton's third law of motion. One will say that, oh, but say, there are forces acting on them. Yes, FA, FB, but the two forces cancel out, nullifies each other. So it appears there's no force acting on them. Please, are we okay?
Yes, please.
So we have just used Newton's third law of motion to prove the law of conservation of linear momentum, that in the absence of external force acting on a system of colliding bodies, the sum of momentum before collision is equal to the sum of collision momentum after collision. Or in the absence, okay, let me put that down for you. Okay, let's do some writing so I can also conserve. This I won't conserve momentum, but energy. When we finish, we'll also use the third law, second law of motion, to prove the law of conservation of linear momentum. So this law says that in the absence of external force, in a system of colliding bodies or interacting bodies, the sum of momentum before collision is equal to the sum of momentum after collision. So this law states that in the absence of external force acting on a system of, please check the input, acting on a system of colliding bodies, the sum of momentum before collision is equal to the sum of momentum after collision. Or when the net force or the external force acting on a system of colliding bodies is 0, momentum is conserved. There are different ways of crafting it, but the whole thing is that the external force acting on a system of colliding bodies must be 0, and when that is 0, momentum will always be conserved. If momentum is conserved, it means that initial momentum is equal to final momentum. Please, are we okay?
Yes, please.
If you have any question, quickly ask. Before we are going to using the second law to prove the law of conservation of linear momentum. Okay, so let's look at how we can use Newton's second law. So using Newton's second law of motion to prove the law of conservation of So using Newton's second law of motion to prove the law of conservation of linear momentum or momentum. Okay, so Newton's second law, this is what it says, that force is equal to change in momentum, the rate of change of the rate of change of momentum with respect to time. So dp over t. Okay, now let's assume we are dealing with one body for one body or for a single mass. We can relate it to this. F is equal to change in momentum S for one body. So the constant mass times velocity minus initial velocity, final velocity minus initial velocity, all divided by time. Please, are we okay? Hey, are you tired?
Yes.
No.
Yes.
Okay, then give me a feedback. Okay, so for one mass or for one body, this is it. Now, if let's cross multiply F by T is equal to mv minus u. Now, in the absence of any external force, this is impulse, but when there is no external force, F is equal to 0, then the left-hand side impulse will be equal to 0. So we have 0 is equal to mv minus mu. Therefore, we have mu is equal to mv. Mu is equal to mv. Class, what is mu?
Initial momentum.
This is initial momentum, and then mv is final momentum, telling you that when there is no external force acting on, okay, a body, then its initial momentum is equal to its final momentum. If it's about two different masses, so we've proven it, but this is about for one mass or a body. If it's about two different masses that are interacting with each other, are you done writing? So I could change the direction of the camera. Are we? If you are still writing, let me know.
Please, you can do.
Okay. I just want to change the direction of the camera. So if it's about for two different masses, A and B, then so if we have two bodies that are interacting with each other, then Newton's second law is saying that F is equal to the rate of change of momentum of A delta P of A with time plus delta P of B with time. So we have change in momentum mass of A times V of A minus U of A over T plus delta P of B, change in momentum of B, M of B, V of B minus U of B, all divided by T. The T for A, they are in a state of collision. They are colliding with each other. So the time of impact is the same. That is why T is the same for A, T is the same for B. So when we multiply through by T, we have F by T is equal to T by this. So the T's will cancel out. And so we'll end up having MA VA minus UA plus MB VB minus UB. Now, in the absence of any external force acting on a system of colliding bodies, when F is equal to 0, we have 0 is equal to, let's expand, ME VE minus ME UE plus MB VB minus MB UB. Let's have all the U's at one side and all the V's at the other side. So this and this will cross the equal sign. So we have ME UE plus MB UB equal to ME VE plus MB VB. This is the sum of momentum of both bodies before collision. So summation of momentum before collision is equal to summation of momentum after collision. So we have proven the law of conservation of momentum for two interacting bodies using Newton's second law of motion. This is so examinable. You can be asked to use either the third law, Newton's third law of motion, or Newton's second law of motion to prove the law of conservation of linear momentum. Please, is that okay?
Yes.
All right. Let me see if we can get some questions to solve. Can I clean the board or you are still writing?
Please, yes.
Okay. So you let me know when you finish writing, okay? Can we continue?
No.
All right, please hurry up. Okay, so
Please, I'm not done.
Akusha, hurry up.
Yes, please. Thank you.
Akusha, are you through?
Please, I'm almost through. You can start cleaning from the top.
But not from the down.
No, please.
Okay, so I earlier was saying that when the product of the force acting on the body and the time taken for the force to be exerted on the body would give you impulse, okay, which is also equal to the change in momentum. So we said impulse I is equal to the change in momentum delta P.
Steady, please. I'm done. Thank you so much.
Change in momentum, which is delta P. We can plot a graph of the force acting on a body or the force exerted on a body against the time taken for the force to be exerted on a body. Now note that when you are given a graph of force and then time is always an independent variable, it doesn't depend on. So all in graphing, independent variables are always plotted along the horizontal. So if you plot a graph of force against this, the area, if the graph is a straight line like this, the area under the graph is certainly equal to, so area under a force time graph, a force dash, a force slash Newton dash time slash second graph is always equal to the total impulse or the total change in momentum. So area under a force time graph is always equal to the total impulse I, or which is also equal to the total change in momentum. And this is because we earlier saw that I is equal to delta P. So the area under the graph is equal to the total impulse, which is also equal to the total change in momentum. Now, if the graph is if the graph is plotted and the area looks like, the area under the graph looks like a triangle, okay, don't forget that this area can be determined using the area of a triangle. Area of a triangle, which is half base times height. So this is the height, this is the base, okay. So determining this would give you the area of this triangle, and the area of a triangle under a force time graph is equal to the total impulse, which is also equal to the total change in momentum. So take note. If the area is a rectangular something, if it's a rectangular something, a force time graph, and then the shape is a rectangular shape, then don't forget that the area under this rectangle or graph would be equal to the total impulse or total change in momentum. And here, this is a rectangle. So you determine the area using the area of a rectangle. Please, are we okay?
No, please.
Am I yes or no?
No, please.
What I'm saying is that we can plot a graph of force acting on a body against the time taken for exertion of the force on the body. So a force time graph, okay, the area under a force time graph would give you the total impulse or total change. But if the area is like it's a triangle, you use the area of a triangle to determine that area. And so whatever you have as the area of a triangle will be equal to the total impulse or the total change in momentum. If the area under the graph is a rectangle, of course, you need to use area of a rectangle to determine that particular area. And this would amount to the total impulse, or if it's a circle, the same way out. But the whole thing is that the area of a graph of force time graph is equal to the total impulse. Are you okay? Okay. In collisions, in collisions, when two or more bodies are colliding, are in a state of collision, the collision can either be a head-on collision. Okay, we can either have a head-on collision or sideways collision, what we sometimes call as oblique collision. Inside in head-on collisions, the two colliding bodies must come from opposite directions. This is to the west, and then the other one, the other colliding body, assuming this is A, this is B, this is due west. So A is due east and B is due west, and they are in a state of collision. Now, assuming that this is mass of A, MA, this is mass of B, MB. A is with a velocity UA. B is with a velocity UB. Okay. P of A, momentum of A is equal to MA UA. P of B, momentum of B is equal to MB UB. Now, just as we saw in when two forces act oppositely, okay, the resultant force is always in the direction of the larger force. A force FA, FB. When they interact, the resultant force is always in the direction of the larger force. Okay. In the same way, when two bodies collide or interact, the resultant momentum is always in the direction of the larger momentum. So let's assume that PA, momentum of A is greater than momentum of B. Then it means that if we are to establish the law of conservation of linear momentum, this is how momentum of A and B before collision. So P of A plus P of B must be equal to P of A plus P of B after collision. But here, since they are in the opposite directions, momentum of A is equal to MA times initial velocity of A. So if you are assuming that momentum of A is greater than momentum of B, then we negate the momentum of B because it is in the opposite direction. So M of B times U of B for summation of momentum before collision. So when the two bodies are moving in opposite directions, then we subtract the lesser momentum from the larger momentum. Class, are you okay? Are you there?
Yes, please.
This is equal to, momentum is conserved. So M of A times the final velocity of A plus M of B times the final velocity of B. One may ask, why isn't there a minus sign? The reason is that if two bodies are coming to collide, body A, body B, okay, just before collision, you can easily determine their direction. But until they have actually collided and you have seen them moving either in one way or you cannot tell their directions. That is why after collision, there is plus. There's no minus after collision. The values of VA and VB will determine whether they would be moving in opposite directions or they will be moving in the same direction. So until you have found VA and VB, you can't tell whether after collision they will be in the same direction or in opposite direction. But before, you can always look at them and tell. Class, are we okay?
Yes, please.
So this is the law of conservation of linear momentum when two colliding bodies are moving in opposite directions. When they are moving in opposite directions. Now, when they are moving in the same direction, oh, look at it. I think this is the last part we are going to discuss. Then we call it a day. So please pay attention. A is in this direction plus colliding with the body B. This is one body just running to catch on the other one and then hitting it behind. So sideways collision. So M of B. This is U of A. This is the velocity of B. If I want to determine the momentum of A, M of A times U of A, momentum of B would be M of B times U of B. So if I want to establish the law of conservation of momentum, since they are in the same directions, I have to sum up their individual momenta. So the momentum of this plus the momentum of this would give me the sum of momentum before collision. So MA UA plus MB UB is equal to sum of momentum after collision would obviously be MA VA plus MB AB. So if they are moving in the same direction, then you add their individual momenta and equate it to the sum of but when they are moving in the opposite direction, you negate the lesser momentum from the larger one or the lesser momentum from the larger one. Please, are we okay? Are we okay?
Yes.
please.
Okay. So, please, Monday, we'll have a class. Monday, we'll have a class. So, take note. We'll continue this on Monday, where I think Monday we have to apply this in solving questions. Then we look at types of collisions. In fact, there are a lot of tricks within types of collision, elastic, inelastic, perfectly, blah, 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 blah. So please do not absent yourself. Okay, make time to be present because we're going to do a lot. Okay, so this is where I'll end today's show. Please, I gave you assignments, trial works. Do them and then let me hear from you. Okay, so until Monday from, I think, 2 to 4 o'clock. In fact, take care of yourselves and then bye-bye to each one of you.
Bye.
And tell your friends that we've resumed after Xmas, so they should come. All right, see you.